I've gone through about 3 or 4 iterations of this talk over the past couple weeks, and so we'll see what comes out today. I hope everything is smoothly worked out now. And so it's more going to be not necessarily about sampling, but applications of witness sets. So David introduced witness sets earlier today, and that's sort of the foundation of numerical algebraic geometry. What can we do with them? And of course, there we go. Okay, so first I'll sort of give you some kind of musings on numerical algebraic geometry, what goes wrong, what goes right, how do you fix things. Then we'll look at witness sets and applications of sampling at the end. So Albert Einstein has a famous quote, "In theory, theory and practice are the same. In practice, they are not." So in theory, Bertini is going to work every time I try it. And in practice, it often has some failures. So the key thing is to understand why you have the failures, how do you fix them, what went wrong, and be able to learn from there. Okay, so the first several slides will be about theory versus practice. So suppose I have a univariate polynomial, and I want to test whether it's identically 0 or not. Is this the 0 polynomial? And so theory says that if I can pick a general x star in the complex numbers and evaluate my function there, and if I get 0, then that's an equivalent statement. So I have the 0 polynomial if and only if I evaluate at a general point, I get 0. So theoretically, if it's non-zero, then the variety is a finite set. Hopefully you can see there are 6 points here inside of this. I did that on purpose to make them 1 pixel big. So you may or may not be able to see them, but it's done on purpose. Okay, so hence the complement is this risky open dense subset. And the way I like to think about this is imagine you blindfold someone and you give them some mind-altering medication, alcohol, drugs, whatever. And then you hand them a dart, okay, with a nice sharp point on the end of it. Spin them around a few times, and then tell them to throw the dart. Tell them to throw the dart, okay? Where does it land? It doesn't matter. Okay, so it's going to land somewhere. Hopefully it's not you, but presumably it'll land somewhere, and that's where you're going to evaluate your polynomial at. So f is identically 0 if and only if it's 0 at this randomly selected point. And we put this quantifier on there with probability 1. So numerical algebraic geometry methods are based on probability 1 statements. Of course, I haven't told you what my probability distribution is, but you can imagine that you have a blindfolded person, spin them around, they're going to probably give some kind of nice distribution on there. Okay, so that's the theory. What happens in practice? So what happens in practice is, David mentioned this earlier. Do you know this polynomial exactly, or do you only know it approximately? If it has complex coefficients, are those known exactly, or are they known approximately? Can you rescale the function? Does it have nice scaling or not? Suppose I put 10 to the minus a million times f. Theoretically, that has the same roots as the original one, but they behave numerically much different. How do I select a random point? How much error is there when I'm evaluating at this random point? What does it mean to be equal to 0 in the presence of error? If I use floating point arithmetic, I only have finitely many points I can sample from. How do I connect this all together? And even though we say that it works with probability 1, with all of these things taken into account, there is a positive probability of failure. And so now, instead of little dots that you can't see, you now have things that have area, and there's a positive area associated to them. And so now there is a chance that your dart will land in those. So how do you handle that? Well, you go to higher precision. David showed this very nicely in his talk. 16 digits wasn't enough. He went up to 26, and now you get a much better picture of what's happening. You can rescale your polynomial. So if you have crazy scaling, you want to rescale it so some norm is 1. Reformulate. So David mentioned this earlier. You have to think about, how do I actually formulate this polynomial system? Many times you can formulate it in different ways. Sometimes geometric, sometimes algebraic. You have to adapt your formulation to what you're using to solve with. What algorithm are you using? Find a formulation that fits nicely with that algorithm. Take advantage of structure. So if you have structure in your system, if it's sparse, if there's group actions, try to take advantage of that. And sometimes all of the current methods fail. You get to develop your own method. And Simon's poster is a different approach to be able to solve high degree polynomials, and I believe his poster is on in the plane. So those kinds of degree 170, those freak me out. I would not want to touch them using Bertini. And so you have to develop a different approach that can be able to handle the high degree nature of that. Okay, so let's start with a very innocent looking question. Is the variety, so x and y are variables, epsilon is a parameter, is the variety xy minus epsilon reducible or irreducible? So in theory, you have this answer. It's reducible if epsilon is equal to 0, and it's irreducible if epsilon is not 0. In practice, what we say is this is an ill-posed problem and you give up. Okay? So ill-posed, one thing is you have to have this continuous behavior on your parameters, and this is not, the answer is not continuous in epsilon. So what happens if you want to solve an ill-posed problem is you have to think carefully, how can I make this a well-posed problem? So if my parameter epsilon is non-zero, is it non-zero because of numerical error, or is it truly a non-zero number? So this is where the user has to know these kinds of things. If it's non-zero because of numerical noise, well then you just set it to 0 and it becomes reducible. Now it's a well-posed problem. If it's non-zero, that means you can divide by it. And so what you should do is you should rescale your system. You can divide by epsilon and now add new coordinates that just rescale your original ones, and you get xy minus 1. Now you see that this is clearly irreducible. So you turn your ill-posed problem into nice, well-posed things. But this requires users to think. Okay, so for numerical methods, the ideal case, well-posed problems, continuous in your parameters, well-conditioned. So your condition numbers are nice, which means you're far away from bad behavior, and then numerically stable. You're allowed to put small perturbations, and your answer doesn't change very much. So this is what I'm looking for a numerical problem. I need these three things to be able to solve it robustly and efficiently. Okay? And so when someone emails me a polynomial like this, I just want to scream. Please don't try to put a polynomial like this into Bertini. It's not going to give you nice messages. I was emailed something similar, but I couldn't find it in the time frame from yesterday to today, and so I found another one that I could. But yes, I have many systems that are much worse than this. So what makes me scream even more is when these are floating point numbers. And they come about by putting things in and then expanding out. As we saw from David's talk today, expanding out is the worst thing to do. Now you put floating point numbers and you expand it out and you truncate because of finite precision. And this thing is just a mess. There's
worse, they have exact coefficients, and they turn them into floats for their program.
Right. Right. So, yes, I get emailed things like this, and it's like, why didn't Bertini work on this? It's pretty clear why it didn't work. Okay, so here's another theory and practice question. What's the difference between these two polynomial systems? Okay. So one has two equations, one has one equation. So theoretically, the origin is isolated of multiplicity 200, and G defines a positive dimensional component, a parabola. What happens in practice? In practice, suppose we look at some region, so say part of the parabola. Of course, G vanishes on that part, and F, to some extent, looks like it vanishes on there, 10 to the minus 60, pretty small. So what is the difference? The difference is WD-40. I'll explain this in a second. So free sticky mechanisms. So if this comes from a mechanism problem, the difference between these two is you just need a little lubrication to be able to make it move. Otherwise, the machine will look exactly the same. So you have to really view, what am I trying to do with this system? Does it match reality, or is it an approximation of reality? And so let me give you a concrete example of this. Not multiplicity 200, but multiplicity 4. So there was a computational kinematics workshop in 2001, and Park from Seoul National University, as part of this, they gave demonstrations of their new mechanisms that they developed. And so here is his mechanism that he developed. And he could actually put a controller in there, and it was highly accurate. You could be able to move this center point accurately around this object. When you go to the theory says it's isolated of multiplicity 4. It should not move, but it does. And the reason is well, things behave. Well, high multiplicity, joint tolerances, so things aren't exactly rigid, they're approximately rigid, and then you have a little bit of link elasticity in your mechanisms. So you spray a little WD-40 on this, and it behaves just like it was a positive dimensional set, whereas the theory says its multiplicity is 4. So you have to be careful, especially in applications. What does the theory say, but what does the application really need? Okay, so generally speaking, numerical methods prefer well-constrained systems of low degree. Generally speaking. Okay, Simon's poster is a completely different story, but generally speaking, if I was going to create my ideal system, it would have quadratic equations and really nice. Coefficients of roughly unit magnitude. So well-constrained means that the codimension is equal to the number of equations. And so in that case, I can perturb my coefficients, and I have stability of my solutions under perturbations. So here I have an overdetermined system, 3 equations and 2 variables. They all intersect at a point. If you would take a random perturbation of those, they no longer have a solution. However, if I would only take 2 lines, say the green line and the blue line, they intersect at a point, and the green line and blue line still intersect at a point over here. It just moved a little bit. So it's a well-constrained system. It's stable under perturbations. Whereas when I take an overdetermined system, it's unstable. You lose your solution. Grosvenor basis methods, on the other hand, again, generally speaking, prefer vastly overdetermined systems. And the reason for that is once you have a lot of the equations already, you don't need many more to get a Grosvenor basis. You may already have enough for the Grosvenor basis. So Grosvenor basis methods, as we learned yesterday, are doubly exponential. But if you can give me more and more polynomials, they actually turn into polynomial time algorithms. And so if you can find lots of polynomials that vanish, vastly overdetermined, Grosvenor basis methods are great. Good. The other thing is that when you do an exact computation with Grosvenor basis, you get a proof out of it. You have no floating point error. You have a proof. Coming up with a proof, as we know from paper proofs, can become somewhat difficult. So a computation coming up with a proof can also be somewhat difficult. Numerical algebraic geometry gets away from proofs by putting on this probability 1 quantifier. We think we've selected random numbers that will work, but we have no proof that our random numbers are generic and will work. Okay, so how to represent an irreducible variety on your computer. So one thing that we have now is we have computers. They're everywhere. Many of you have them out now. You can do computations on them. How do I turn this variety into something that Frank's computer can read and understand? Okay, so algebraically, we have this prime ideal. We look at the set of all polynomials that vanish at every point. Hilbert's basis theorem says there exists a finite set of polynomials that vanish there. And we can turn this finite set of polynomials into something our computer can understand. It's a finite list of data that our computer can understand. What's the problem? This goes back to the poem of yesterday, The Theology of Hilbert. How do you actually compute such a thing? You know it exists, how do you actually compute it? So that's the difficulty. Geometrically, we represent an irreducible variety by a witness set. And a witness set contains 3 things. First thing I need is some finite set of polynomials. So some finite set of polynomials such that A is an irreducible component. It need not be the only irreducible component, it just needs to be a irreducible component. I need a linear space of the proper codimension, and then, since those will intersect transversely, I need the set of points in the intersection. As was mentioned before, the codimension of the linear space gives you the dimension, and the number of points that you get in this intersection gives you the degree. So you immediately get the 2 invariants, the first 2 invariants of a variety that you would like to compute, the dimension and the degree. Okay, so let's look at the first natural example in algebraic geometry is the twisted cubic. And so here's a parameterized description of it, and then you do the implicitization, and it's defined by these 3 quadratics. That's its prime ideal. This is overdetermined because its codimension is 2, but yet I have 3 polynomials. So if I was going to turn this into a witness set, I would take 2 of those polynomials because its codimension is 2. Pick a randomly selected linear space. I let MATLAB pick random numbers. In Bertini, we pick, I can show you this if you're interested, we pick random floating point numbers with 300 decimal places. I didn't want to write those on the screen. So nice long numbers. And then you compute the points of intersection. And here you have 3 of them. So a polynomial system, a linear space, and the 3 points. I can turn that over to my computer to be able to do computations on this variety. Okay, so just to note, if I look at the variety defined by f, I have the twisted cubic, plus I have this line at infinity. And the beautiful thing about witness sets is they localize the computation to the component that you're on. So the witness set doesn't actually see this line at infinity. It only sees the twisted cubic that it lies on. So it's not quite quotient or saturation, but it's in that spirit that we can localize to our component. And one thing that we'll do a lot of with the time sort of towards the end of this talk is we'll move this linear space. Remember, I chose this linear space. So I'm free to choose a different linear space. And then I can just do a homotopy from one linear space to the other, just by changing the coefficients. So I can move this linear space around all that I want, track the solutions as it moves, and I can give you as many points as you want on this variety. The whole goal of numerical algebraic geometry is trying to use a witness set to do computations on a variety where you don't necessarily have defining equations. Okay, so there are many things that you can perform, many computations you can perform with witness sets, and I don't have time to go through all of them. Some of them are listed in these two books, and then even our book came out in 2014, and even since then there have been many more applications. So I apologize for not going through everything, but here's some sampling of things that you can perform with witness sets. So the first thing you can do is you can test whether a given point lies in your variety or not. Remember, you don't necessarily have equations that cut out precisely your variety. So we want to be able to test this with just a witness set. Okay, so here's my original variety. Let's say it's a parabola. Here's my line, and here's my test point. I want to test whether it lies on the variety or not. So what you do is you pick a linear space that passes through the point that you're trying to test. Okay, so pick a general linear space that passes through that, and then do a homotopy from this line to that one. And so this tracks two paths. The yellow point goes to the purple point, and the yellow point goes to the purple point. X star is in your variety if and only if it's one of those endpoints at here. So you have a finite test to be able to determine membership. If X star was this point, then obviously it's there, but since X star in my picture is over here, it's not in there. So this can be performed without knowing any polynomials in your ideal. Okay, the next thing that we want to be able to do is projections. So suppose I have a witness set for A, and I have a projection map, and I want to compute a witness set for the projection, for the image. And we'll actually do this during the software demo, so you can actually see how to do this in Bertini. Okay, so what you do is you want to slice down here in the image. So you want to be able to slice down there. But I don't actually have polynomials that vanish down here. So what you do is you lift that up to a linear space that intersects your variety upstairs. Now I have a linear space, and I just deform from this generic linear space to that one. So I just changed my linear space from an arbitrary one to essentially one that's perpendicular. And for the people that are paying attention, notice here that there's 3 points, but over here there's 2. The third one went to infinity. So it could be that the degree of your image is less than the degree of the original thing. And as you do the homotopy from an arbitrary one to a vertical one, solutions can go off to infinity. Now you perform all your computations upstairs, and then you can just use the image map to project down to have those points downstairs. And you can do this all without any knowledge of polynomials that vanish on the image. Next thing that you can do is you can do intersections. Suppose I have two varieties, and I have witness sets for each one of them, and I want to be able to intersect them. So David mentioned a special case in his talk, which is regeneration. Suppose I want to find the solution set to k plus 1 polynomials. What I could first do is find the solution set to k, and then intersect it with the hypersurface defined by the k plus first. So regeneration was from my PhD thesis, and then several years later we realized, oh, we can do this much more general, you know how things always work in that way. And so we can now think of this as just an arbitrary intersection. The nice thing is these could be components of the same polynomial system. So you could have the same polynomial system f that vanishes on A and B and be able to intersect them inside that same system. Other things that you can do is suppose you want to compute the singular points of your variety. So starting with a witness set for A, you intersect with the singularity conditions. The rank of the Jacobian drops. You can compute the critical points of an optimization problem. So this has shown up several times. Once you have a witness set for your variety, you intersect it with the Lagrange multipliers or however you want to formulate your critical points. So here's a picture of minimizing the distance from this point to the twisted cubic. There's lots of critical points of the distance function, and then you can find the global minimum. And the nice thing is that Seidenberg realized this in the 50s. This is a nice way to get real points. Is you start with a real point that you test from, and you find the global optimal solution of the distance function, and that will be a real point if real points exist. So you can use witness sets, even though they're defined over the complex numbers, to get information about the real numbers. During today's software demo, there'll be much more on real solutions and demonstrations of that. Suppose you wanted to do some algebraic computations. So 3 things that you want to know. Is your variety arithmetically Cohen-Macaulay? Is it arithmetically Gorenstein? Is it a complete intersection? You can do these 3 computations without knowing any polynomial that vanishes on the ideal. You can do these by witness sets, and what you do is you compare a witness set with a general curve section, and just by looking at those 2, you can answer these 3 questions. So one highlight of that is this variety. So for those that have been around long enough, there's a so-called salmon problem, and this is related to the so-called salmon problem. So you have the 4-secant variety of C3 cross C3 cross C4. Please forgive me, let's treat this projectively inside of P35. And so its dimension is 31, its degree is 345. Through lots of work, it was known that there was 10 polynomials of degree 6 and 20 polynomials of degree 9, but it wasn't known whether they generate the ideal or not. Numerical algebraic geometry comes to the rescue, and what we showed was indeed that A was arithmetically Cohen-Macaulay, and those were exactly the generators that you need. So even though you couldn't symbolically do this, you can write these down. I think Luke Oding has these polynomials on his website. They may be several megabytes long, so they're not nice polynomials to look at, but we can do computations on this without looking at those polynomials. So that was a nice success story of numerical algebraic geometry.
So you do this computation because this is parameterizable?
Yes. So all you need is a witness set, but since it's parameterizable, a witness set is much easier to compute. Okay, so in the last part of my talk, I want to now tell you about sampling. So we can move this linear space around and generate sample points. How can we extract data from those sample points? So one thing I'll mention is about how can we find polynomials that vanish when we don't know any of them that vanish a priori. Describe sampling for sums of squares programs, and show how sampling allows you to solve these much faster. Degree estimation, so David talked about a 4-bar problem. I'll mention the 6-bar problem. And then if there's time at the end, I'll tell you how you can recover topological properties from sampling. Okay, so this is something that I didn't appreciate too much as a graduate student. I thought that every variety you knew its defining equations. And then I was slapped upside the head and realized there are many varieties that appear out there in nature that we have no clue any polynomials that vanish on them other than the identically zero polynomial, which vanishes on every variety. Okay, so here's an example of a problem that we were sort of interested in. We wanted to, or the main problem is compute the exponent of matrix multiplication. So the 30-second short version is it's the number such that describes the number of arithmetic operations it takes to multiply two n by n matrices. And so it's sort of the lim sup of this exponent here. And it's known to be bounded below by 2, and the upper bound somewhere is in 2.3, something like that. If you read James Landberg's recent book, you know that this problem could be solved if we could know every polynomial for every secant variety. So if I could know every polynomial for every secant variety, I could just test this and be done. All right, then you start in trying to do this. The n equal to 1 case is trivial. We know how to multiply two numbers. It takes one multiplication to multiply two numbers. Good. And then you go to the 2 by 2 case, and you're already stuck. So 2 by 2 has 4 elements, and so this is the secant variety you want to consider. So you want to look at the 6th secant variety of C4 cross C4 cross C4. Slight abuse of notation. Let's treat this projectively inside of P63. It's not closed, so you have to take this risky closure. And now you have a variety, and it's easily determined that its dimension is 51. Just if we're unclear about the notation, this is the outer product or tensor product. So that if you have 3 vectors in C4, then this defines a 4 by 4 by 4 tensor, which is represented here. And the ijk entry is just ai times bj times ck. Okay. So here's a variety where in the time we were, before we started looking at this, no known defining equations existed. So we could formulate this as a classical elimination problem. So using what Carlos and David talked about yesterday, this is a very natural elimination problem. Here's my defining equations, and these are my variables z, and I want to eliminate all the a, b's, and c's from there. I'm still waiting.
So it didn't fill up the memory of your computer?
Yeah, that's what happened. It filled up the memory. I tried a larger memory computer. It filled that one up. I'm still waiting on a computer with enough memory to compute this. So, okay, we're still waiting. Maybe someday it'll work. So then let's try something else. Let's try to treat this as an interpolation problem. So if I could sample points, which I know how to do, I can just use my witness set and move my linear space around so I can compute sample points. And now I want to compute polynomials that vanish on there. So that means just doing a linear algebra problem. Okay, so here's some points on the twisted cubic. Let's say I'm looking for quadratic polynomials. So then you do the Veronese embedding of degree 2, you get some matrix, and all you have to do is compute its null space. Well, this one's very nice because it's binomial, so this column is equal to that column, this column is equal to that column, this column is equal to that column. So you can very naturally see the defining equations out of it. Okay, so now you come back to reality and you go, okay, how many points do I need to sample to make this work? We were looking for degree 18 polynomials. Why? I don't know. JM told me look for degree 18. Well, I think the reason is 3 times 6 is 18.
Well, there's a representation.
Yeah, exactly. Yes. Okay. So then I sit down and, okay, how many points do I need? 4 times 10 to the 17th. That's not going to happen. And so I told JM that this isn't going to work. And he said, well, try something else. Just give me anything you can give me. And I said, okay, partial information is better than no information. Right now we have absolute nothing. If I could tell him just something tiny, it may work. And so the idea was, well, it's a classical idea. Instead of trying to interpolate the whole variety, why don't I just interpolate the witness points and look to see which polynomials vanish on those witness points? Obviously, if it vanishes everywhere, then its restriction vanishes on that set of points. The nice thing is that there's an exact correspondence between vanishing on A and vanishing on the witness sets when it's arithmetically Cohen-Macaulay. And in general, you can just get upper bounds. So you know that everything that vanishes on A vanishes on the witness points, but stuff that vanishes on the witness points need not lift up. Okay, so I tried this, and now I only need 7,000 points. My computer can do that. My laptop can do that. I didn't even need a supercomputer to do this. The degree is 15,000. I only need 7,000 of those points. And there's no polynomials of degree 18. All right, so then I'd say, okay, nothing of degree 18, nothing smaller. Let's go to 19. Maybe JM's calculations were off by 1. And sure enough, in degree 19, there were 64 polynomials that vanished on that linear space. And so I walked up, I was at Texas A&M at the time, I walked up to JM's office and I told him, I think there's polynomials of degree 19. And in 30 seconds, he knew exactly what they were, and he had a description for them, and 64 was the correct answer. All he needed was tell me where to go look. I don't know if this is right, but I at least know this is where you should look at. And amazing, 64 is 4 times 4 times 4. 19 is 4 plus 4 plus 4 plus 3. And from those two equations, you can define the 64 polynomials using representation theory. And lo and behold, they work.
So the reason this worked is because you use this dimension reduction you get by slicing.
Correct. Correct. We didn't just sample arbitrarily. We sampled along a linear space. And so that reduced the dimensions. And so now we know, at least in the 2 by 2 case, we have a complete description. The rank and the border rank are 7. Open problem, highlight from Friday. I'll take my 2 minutes from Friday. 3 by 3 case is unknown. Okay, so if you want a problem, what's the rank and border rank of 3 by 3 matrix multiplication? There are bounds that are known, but it's not anywhere settled. Okay, so what we were doing was we were interpolating over linear sections of your variety. What happens instead of interpolating over linear sections? I interpolate over sums of squares modulo my ideal. Okay, so instead of looking at interpolation over linear spaces, interpolate over sums of squares modulo your ideal. Diego and Pablo recently described a method to be able to do this. And the beautiful thing of this method is it just uses sample points. You don't actually need to know what any polynomials are in your ideal. All you need is a way to select sample points from your variety. Okay, so here's the problem. Suppose that polynomial can be written in this way. Compute its decomposition.
How is divided given to you?
See, this is the difficulty. If it was given to you in equations, you would have it. But many times it's an image of something. So that's very naturally, secant varieties. So that's what they were mainly focused on. Yeah. Okay, the reason they wanted to do this was they wanted to have a certificate of non-negativity over the real sets of some variety. So if you can write P as a sum of squares modulo the ideal, sum of squares are always non-negative, and so you have a certificate of non-negativity. Okay, so what they do is they replace the original problem with a necessary condition. So instead of trying to have these equal everywhere modulo the ideal, they pick sample points. Now those sample points essentially, not exactly, but essentially encode the ideal, and then you just need equality between your polynomial and the sums of squares on those finitely many points. Now, sums of squares can be really nicely represented using semi-definite programming. So you can solve this problem using semi-definite programming. Okay, so here's an example from their paper to answer Alicia's question. Here's one of the varieties that's actually given to you with some defining equations. So you want to look at symmetric matrices which are idempotent and their trace is equal to k. That's a nice variety. Take the Zariski closure of that. It's a nice complex variety. And what you want is you want to look at this trace ratio, and you want to know how large can I make gamma such that this function can still be certifiably non-negative on this set. Okay, so x, y, and z are given matrices that they selected. So they wanted to know how big can gamma be such that this polynomial is certifiably non-negative. Good. They tried to compute a Grosvenor basis for this, and through different n and k, they were successful, started to run out of memory at some point. But the beautiful thing is we can sample this variety, and so we don't need a Grosvenor basis or other defining equations. We can just use those sample points. If you use the defining equations that you have here, you can get a semi-definite program. And the key thing is not necessarily what the data is, but look at the comparison. By using sample points, you get a much smaller STP, many fewer constraints, and the time is much faster. Okay, so next example of using sampling is suppose I have a variety of unknown degree, and I want to estimate its degree. And in particular, this is the problem that my student has been looking at. So in the 4-bar case, David talked about the 9-point problem. You want the coupler curve to pass through 9 points. Go to the 6-bar problem. So here's a 6-bar. Instead of passing through 9 points, suppose I also wanted to have a certain pose at them. So now I want it to be a point as well as a pose. Each one of those imposes 2 conditions. There's 16 degrees of freedom, and 16 divided by 2 is 8.
So I thought it was 15 degrees of freedom.
Yeah, because this one is free.
Where your hand is pointing.
Yeah.
Gotcha, okay, thanks.
Yep.
I missed that.
Yep, exactly. So you can write down upper bound. So on the board here, I have multi-homogeneous Bézier bound, 3 times 10 to the 10th. So if we were going to set up a straight line homotopy, as David talked about today, we would need to track this many paths. I have an upper bound. It's finite. But Still not good enough. Okay? So just to give you a sense of what happens in the 4-bar case, so if you would do the same problem in the 4-bar case, now you need 5 poses, and this was solved in 1886 by Burmester, and there are 4 solutions to that. He did this by hand. Students can do this by hand. It's really an easy problem that you can solve. Good. So without computers. All right, so 4-bar case, 4 solutions. 6-bar case, we don't know how many solutions. But here's what we're going to do. We're going to use monodromy, which was talked about in David's talk, to be able to estimate the degree of the variety. Okay? So, just a reminder how this works. Here's the same variety that's up there. We're going to intersect our variety with a linear space, and suppose we only know one of those points. And now what we're going to do is we're going to move our linear space around and see what happens to that solution. Sometimes, if I just do a little loop here, I come back to myself. If I do a bigger loop, then I pass through the branch cut and I end up here. You can also do this for the cube root as well, and it's kind of fun to be able to track the solutions all the way around. There's some recent software called Monodromy Solver in Macaulay 2, so it's a Macaulay 2 package that you can actually use to solve your polynomials using monodromy loops. Once you know one point, and it's an irreducible variety, you can find all of the other points by doing enough monodromy loops. At least, that's the theory. So there's 2 recent, sorry?
Practice.
Exactly. It works well in practice as well. So there's 2 recent papers that describe this, and it's a Macaulay 2 package, so you can just download it directly from Macaulay 2. Okay, so here's a big if. I can assume anything I want. Okay, so let's assume that if I can do this, if I take a finite set of points and I go around, I get a random subset of the same witness set. So assume that I can generate random subsets of the witness set. Don't crucify me. I know I cannot do this. But let's just make believe we can. Okay? Make believe we can do this. How could we use that to estimate how many total points there are? So there's a classic problem of this, and it's called the German tank problem. So the Allied forces wanted to know how many tanks Germany was producing a month during World War II. Once you know how many tanks you have and you know how many you've blown up, you kind of know how many are coming back to kill you. So what they did was they found serial numbers on the parts that they recovered from the blown up tanks. And they assumed a uniform distribution of those serial numbers. Obviously, this is a wrong assumption, but it's a model. Okay?
All the odd number of tanks had weak tracks.
Right, exactly. Something went wrong. Or the place where you blew up tank, they came right off the assembly line right after another. They're not uniform. But let's assume they are. Let's be statisticians for a little bit. We know our model is wrong, but let's assume it anyway. Okay? And it's amazingly accurate. The Allied forces, of course, had intelligence operatives, and they were reporting that in 1940, they were generating 1,000 tanks a month, and then they ramped up production in 41 and 42, and were near 1,500 tanks a month. Those were the intelligence estimates. From the recovered tanks, they looked at the serial numbers. The statisticians said, about 170, 250, 320. After the war, they went back and looked at the actual records. Germans keep absolutely wonderful records. As long as they're not blown up or burned down, you can get access to them. And it was amazing that the statistical analysis was much more accurate than human intelligence that was happening. Okay, so even though your assumptions are wrong, you still can get data. So in our assumption, we assume that we can get random subsets. And so then we apply a hypergeometric estimation. And it's a really simple formula. You take the number of points that you know, divided by the ratio of repeats when you come back. Okay, so just illustrate. Suppose I know 10 points, and I use them to generate 10 new points. If, when I come back to this new set of 10 points, I have 8 new ones and 2 repeats, my ratio of repeats is 2 over 10, and so I can estimate about 50 solutions. Okay, very simple, very naive formula. So let's try it out on a problem that we already know the answer to. If I fix these 2 pivots, that removes 4 degrees of freedom. So then I need to remove 2 poses, because that's also 4 degrees of freedom. And this was studied already by Plechnik, McCarthy, and Wampler several years ago. So there's some good data available on this problem. Okay, so we took a set of 1,000 solutions that were known and did 10 random monodromy loops. And in those 10, the mean was about 17.5% were repeats. And that gives us an estimated number of 5750. What's the actual answer? The actual answer is 5754. Amazing that we start, I know my model is wrong, I know I can't do this, but it's amazing that even in this estimated framework, it actually gives us data that we can use. Okay, good. So even from 10 loops, we have a very accurate estimate of the number of solutions. So we tried this on the 8-pose problem. We started with 1 point. We did a monodromy loop. It came back to a new thing. And then we took those 2 points, did a monodromy loop. They kept coming back to new points until the 13th trial. And so then we can start to get estimates. And you can see that here's the number of solutions that we have. Here's the estimate. You see that the estimate quickly levels off. We're still trying to get these last few solutions, but at least we now know that we're looking for about 1.7 million solutions. So we had this upper bound of 4 times 10 to the 10th. The actual thing is 1.7 times 10 to the 6th. So our upper bound is off by 4 orders of magnitude, which is very common in kinematics problems. Okay, good. So even down here, when we had very few solutions relative, we still kind of have a very good estimate of the number of solutions. So even if we don't have all of them, we can give you good estimates on the degree. Okay, my last example for sampling is trying to find topological properties. So if you look at these 3 pictures, well, let's look at the first 2 on the left. You should be able to identify what they are of. Okay? Good. So this one should be, even my kids could tell you what that is. They probably won't be able to tell me what that is because they've never seen it. But you at least know from sample points, this gives you a picture that your brain immediately can interpret what it is. We should be able to do the same thing with varieties. If I give you sample points on that variety, we should be able to know what that variety looks like. In particular, we should be able to compute its Betty numbers. So it's connected, it has a trivial fundamental group, and there's one void inside. This has been studied by lots of people to be able to do this. And so you can get topology of real algebraic surfaces that should say varieties, not necessarily surfaces, from point clouds. So you can do this very naturally. Okay, so what is the underlying way to do this? And the underlying method is persistent homology. So you start with your data points as points, and now you treat those as the center of a sphere of growing radius. So there's some points of small radius. Everyone is their own isolated little point. As you grow the radii, they eventually connect and connect again, and then at some point it's just a big mess. Okay, so there are very good software out there to do persistent homology. JavaPlex is one of them. What we can do from a sampling point of view is we can provide provably dense samples. So what that means is that if I have a sample point, I know how far away the other sample points are. So I know when these two things have to link up. I can give you upper bounds on when these two circles have to link up. And so then you can prove theorems about topological features in the point cloud. So we generate these provably dense samples using numerical algebraic geometry, and you can get theorems from those point clouds about the topology. Okay, so here is a surface, and here's a sampling generated by Bertini with this method that we developed. And the topology of it is well known, in particular a trivial fundamental group. The theorem, rather than write down the statement because it would take like 10 slides to write it down, it's better to show it in the picture. Anything in this pink salmon colored region is something that we can prove actually exists. And if it's outside of that region, we don't know. So the way that this works is you have a birth and a death. So when did a feature show up and when did it die? So at this point, you see you have a loop. And then here, the loop is contractible. So it was born somewhere before here and it died somewhere over there. And so you measure how long did something live, and the life that it lived is how far off of this diagonal that it is. So there is a connected component, and then there is this Betty 2 that shows up. And here's an interesting thing. You look at how far it is off this diagonal, and you make judgment estimates whether it actually exists or not. But yet, we have a theorem that says if I'm in here, I know it exists. And so what does this correspond to? This kind of looks like a dumbbell shape. And so what's happening is it sort of looks like two voids, and then those two merge into one, and that's where this one dies. So you might just look at this and say, oh, there should be 2 in dimension 2, but it's not actually in our theoretical region, so it doesn't actually exist. Okay, I am out of time, so this is a great place to stop. Hopefully I shed some light on what makes computations difficult. Solve well-posed, well-conditioned, numerically stable problems. That sometimes takes work to turn your problem into one of those. That's the art form in numerical algebraic geometry, is how do I actually create such a problem? Hopefully I explained witness sets and some applications. There was many, many, many omissions, and I'm sorry. And if you want to see this in action, come back in a half hour, and we'll have some demonstrations. So, thank you. Any questions? Yes?
So earlier you said that you didn't like the idea of a curve of degree 170.
I didn't like a polynomial of degree.
Polynomial. But so high degree is fine, provided you have a way of
Exactly.
parameterizing it or something.
Correct. So this variety here is defined by 70 quadratic equations. I love quadratic equations. I'm okay with 70. I'm not okay with a polynomial of degree 1.7 million. So high degree varieties are okay as long as they're defined in their defining equations in some way are much more natural. Yes.
You know, things can be high degree, but in a high dimensional space can be quite simple there.
Exactly.
And it's only when you drop them down that they become
Exactly.
mass.
When you project high degree things down, now everything is so close to each other that it's so hard to distinguish things. This is in 70-dimensional space. These things are spread out so far that when I slice, the points are very far apart. And so that's a good.
So for the persistent topology, I think that here actually, there is topology is not the compromise with the user metric. Also, would you divide another metric for heuristic topology, or just use the user metrics for calculating the persistent topology?
So here it's based on the question was about persistent homology.
Yes, yes.
And so here you use the Euclidean topology. So you treat your variety inside of Rn, and you look at the Euclidean topology of that.
There's not like there's no singular homology in there's some topology.
Right. Right.
It's also fairly easy to use like
Well, there's
there's topology that you have on projective space as a quotient, so you just define it. It's pretty easy to
Yeah. 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 You can do projective space as well. Did you have a question, Tanner?
Yeah, I was wondering like what's the size of those coin clouds that you're getting, and how many John clicks taken to eat them?
That's the difficulty.
Yeah.
The difficulty is always the number of sample points. And the number of sample points depends upon how close you want your points to be.
Right.
So you want a provable epsilon that's close enough to recover all of the features, but not too small that you get a point cloud that overwhelms the software.
Those figures you reference, those have like provable epsilons in them?
They take different approaches. They take many different approaches to be able to do this. Michael, did you have a question?
What is a provable dense sample?
Yeah, great. I had the definition and I erased it. For every point in your variety, let's say a real point, there exists a sample point, S, in your sample space, such that the distance is smaller than your predefined epsilon.
So just a Hausdorff distance?
Exactly. Yeah, in the Euclidean space. So every point lives no farther than epsilon away from one of my sample points.
How do you handle that if the real points are unbounded?
Yes, so you have to go to a compact subset of it. And then what you do is you find the topology of the compact region. Or you go to projective space and switch to that. Yes, so I should have mentioned that caveat here that this is all done with compact varieties. Yeah, otherwise it would be unbound. The sample set would be unbound.
You can also just SN or something like that.
Exactly, you have to compactify it in some way.
Yeah.
Since you're using Euclidean distances, does this stuff tell you anything about varieties and characteristics at all, or is this just completely nothing?
I will leave that question to one of the more experts, but the problem with characteristic P is measuring distance.
Exactly, no, I know.
And so I believe you get nothing on,
No information.
no information on characteristics.
Part of the matter, the real points are arithmetic.
Yes.
There's no information.
Yes. So it really is,
Characteristics are dependent.
exactly, exactly. We really want things that are
Actual
continuous.
distances that you can measure.
Yeah.
Yeah, I mean, and this has to do with you're using the standard topology, so you better have varieties that have the standard topology. I don't know how to compute singular homology of a variety of characteristics too.
Right. So it really is dependent on characteristics. And with that said, numerical algebraic geometry is dependent on characteristic zero. We need continuous things.
Well, see, it's more than characteristic zero. It really is complex knowledge.
Yes.
It's really over C.
Yes.
It's using the analytic topology.
Correct. Very good. So let's break here, and software will start around 3:30.